Hi and welcome to Upper and Lower Bounds Calculations. Just before we start, a quick reminder that there is a notes jotter available for this video. Just check the description below for a download link and you can work along with me as we go through the video. Okay, so today's video is all about making calculations with values which have already been rounded and looking at the effect of this rounding on the accuracy of our calculations. So to begin with, a wall is measured. The width is 4 meters to the nearest meter. The height is 2.2 meters to one decimal place. What is the maximum possible area of the wall? Well, the first thing we need to think of here is we actually need to think about the width. So the width is 4 meters, but that is to the nearest meter. So I need to think about first, what values could that have been? And so I'm just going to create a little number line. And because it was the nearest meter, that will give me 3 meters on one side and 5 meters on the other side. But this has been rounded to 4 meters, and therefore the important values are actually the ones halfway in between. So halfway on this side will be 3.5 meters, and at this side will be 4.5 meters. Those are what we would call our upper and lower bounds. So the smallest that wall could have been would be 3.5 meters, the largest 4.5 meters. In terms of the height, well, the height was 2.2 meters. And that is in the middle here at 2.2. But the extreme values here, because it was one decimal place, I go one decimal place below, which was 2.1, and one decimal place above, which is 2.3. But again, for the rounding, we would go in between. And so we would have 2.15 and 2.25. So the smallest in height it could have been will be 2.15 meters. The largest in height it could be was 2.25 meters. Now the question here asks us, what is the maximum possible area? Well, if I'm going to get the area, I need to do width times height. Therefore, if I want to get the largest possible answer, well, I need the largest possible width, in this case 4.5 meters, and I need the largest possible height, 2.25 meters. And all we need to do is pop that into a calculator and get our answer. And it comes out as 10.125 meters squared. So next, a car travels 120 miles correct to two significant figures. It does this in 3 hours correct to the nearest hour. What is the minimum average speed the car travels? Well, again, the first thing we need to think about here are the two values that we've been given as rounded values. So we had the distance travelled was 120 miles, but that was to two significant figures, which means it was rounded here at the tens, and therefore we're going to go to 110 one side, 130 the other side. And then for our upper and lower bounds, well, the lower bound will be halfway between 110 and 120, which is 115. The upper bound will be at 125. In terms of the time, it was 3 hours to the nearest hour. And so it will be 3 hours in one direction, but that would give us 2 and 4. So to the nearest hour, it will be between 2.5 hours and 3.5 hours. Now in this case, we're looking for average speed. So speed comes from distance divided by time. Now what we are looking for is the minimum average speed. Therefore, what we want is the smallest possible answer to this question. Now because this is a division, now what I actually need is I need a small number divided by a big number. That is how I would get the smallest possible answer. And so the distance needs to be the smallest possible, which is 115, and the time needs to be the biggest possible, which is 3.5. And so if I calculate that using my calculator, 115 divided by 3.5 is, and it's quite a long decimal, but it's 32.857 to 3 decimal places, and that would be miles per hour. And so the lowest average speed the car could possibly be doing would be 32.857 miles per hour. In the next question, we've been given a right-angled triangle, and we've been told that AC and BC have both been measured correct to 2 significant figures. We need to calculate the upper and lower bound for the gradient of line AB. So the first thing, as always, we need to start thinking about the 2 values that we've been given which have been rounded. And so if we begin with AC, we knew that that had been rounded to 3.2. But that had been rounded to 2 significant figures. Now, what that actually means is it's actually been rounded to 3.20. So if we're thinking about the 2 extreme values, it'll be 3.10 and 3.30. And so the lowest possible value here will be 3.15 and the largest possible 3.25. In terms of BC, well, we knew for BC that it had been rounded to 4.5 centimetres, again to 2 significant figures, so underneath we'll be looking at 4.40 and above 4.60, and so halfway in between our lower bound will be 4.45, our upper bound 4.55. Now, with this question, we were asked to find the upper and lower bound for the gradient. Now, what that means is I need to know what the smallest possible gradient would be and what the largest possible gradient would be. And so, with the gradient, we just need to remember that, again, this is a division because it's the change in y divided by change in x. And so in this case, what we're basically saying is it's the 2 values here, so the change in y and the change in x. They're the 2 lengths that we've been given. Now, if I want to find the absolute minimum, the absolute minimum needs to be the smallest possible answer. And so that means the change in y must be as small as possible. And so that would be our lower bound for AC. It would need to be divided by the largest possible value, which is 4.55 for the change in x. If I wanted to find the maximum, well, I would need to think about something slightly different. In this case, for the maximum, I would need to have the largest possible change in y, and that was 3.25. And that would need to be divided by the smallest possible number, because if I divide by a small number, I will get a larger answer, and so 4.45. All I then need to do is work out what each of those answers is. So 3.15 divided by 4.55 is 0.690 to 3 significant figures. And the maximum, 3.25 divided by 4.45, well, that is 0.730, again, to 3 significant figures. And so, the gradient, if I were to write this as a set of bounds, the gradient is at most 0.730 and at least 0.690. Now I'm actually just going to make a small change here. I'm going to just say that it is less than 7.3, and so the gradient lies between 0.69 and 0.73. Okay, so next we have a wooden block is measured and each side is correct to 1 decimal place. So the height is 3.2 centimetres, the width 2.6 centimetres and the length 0.8 centimetres. And the mass of the block is 200 grams correct to 2 significant figures. calculate the upper and lower bound for the density of the block. Okay, so first of all, let's just look at each of our units. Now, the height, we can think about our bounds again for the height. These have been rounded to 1 decimal place. So the height would be at least 3.15 and at most 3.25. The width would be at least 2.55 and at most 2.65. And the length would be at least 0.75 and at most 0.85. The mass has been rounded to 2 significant figures, and so that actually means it's been rounded at the tens, and so it's actually at least 195, at most 205. So those are our bounds for the actual values we've measured. But then we're asked for the upper and lower bound for the density. And so with density, we need to think about our little triangle, and the triangle is MDV. And so given that we want to find the density, well, the density is mass divided by volume. And that means we're missing something at the moment. We have the mass. We know that that is either between 195 and 205, but we don't yet know the volume. So what we need to think about here is, what is the lowest possible volume? Well, the lowest possible volume would come from multiplying the lowest possible lengths. And so 3.15 times 2.55 times 0.75 gives me 6.024375, and that would be the smallest possible volume for this wooden block. The largest possible, well, that's going to come from multiplying the upper bounds all together. So 3.25 times 2.65 times 0.85, and that is 7.32065 centimeters cubed. Now, in terms of the upper and lower bound, in order to find the smallest possible, I would need to use the smallest mass with the largest volume. So the smallest possible mass would be 195, but the largest possible volume was 7.320625. This, when we divide them together, comes to 26.637 grams per centimetre cube. The upper bound, well, that would have to be the largest possible mass at 205 being divided by the smallest possible volume. So 6.024375. So 205 divided by 6.024375, and that comes to 34.028 grams per centimetre cubed. So the smallest possible mass was the 26.637, the largest possible, the largest density, and the largest possible density 34.028 grams per centimetre cubed. And so then we come to a question about buying floor tiles. So Graham is buying floor tiles. His floor measures 6.2 metres by 3.7 metres, correct to 2 significant figures. Each tile measures 50 centimetres by 50 centimetres, correct to 2 significant figures. He's bought 95 tiles. Does he definitely have enough? Now with this one, we've got to think carefully about what this actually means. Does he definitely have enough? Well, what that would mean is we want to just be sure that if the floor was as large as possible and the tile was as small as possible, well, would this 95 tiles still work? And so what we need to think about first is, what is the largest possible measurement for the floor in terms of area? And so that would need us to take the upper bound of both of those measurements. Now they are 6.2 to 2 significant figures. So that upper bound would be 6.25. The 3.7 would be 3.75. And then we would need to multiply the two together. So 6.25 times 3.75 equals 23.4375 meters squared. So that is the largest possible area of floor that needs to be covered. Now if we want to find the smallest possible tile area, well, that is going to be the lower bound for each of the tiles. They were 50 centimetres, correct to two significant figures. And so in terms of centimetres, that would be 49.5 centimetres times 49.5 centimetres. But in this case, because we're dealing with metres squared in the previous version, I'm actually going to use metres here as well. And so this will be 0.495 metres times 0.495 metres. And if I multiply those together, I get 0.245025 metres squared. So this is the floor, this is the tile. How would I work out how many tiles are required? Well, it is very simple. I just need to divide the area of the floor by the area of the tile. And so I'm just going to divide those two numbers together and see what answer comes out. So 23.4375 divided by my answer is 95.65350474. So he said he's bought 95 tiles. Does he definitely have enough? Well, the fact that we have this little decimal area at the end suggests that he may be just short of the number that he actually needs. If the floor is as big as it could possibly be and the tile as small as they could possibly be, he would actually be short. So no, he does not. And so finally we end with the exam question, and this came from the Edexcel paper in November 2017, and it was on higher paper 3. We get a lot of information to start with. The petrol consumption of a car in litres per 100 kilometres is given by the formula petrol consumption equals 100 times number of litres of petrol used divided by number of kilometres travelled. Nathan's car travelled 148 kilometres, correct to three significant figures. The car used 11.8 litres of petrol, correct to three significant figures. Nathan says, my car used less than 8 litres of petrol per 100 kilometres. Could Nathan be wrong? You must show how you get your answer. Now, I just want to point out with this question, if you were looking at this question in an exam and you thought, I'm not entirely sure how to go about this, the one thing I would always suggest is if you see something like this, a value correct to so many significant figures, straight away what I would suggest is just to write down the upper and lower bounds of that value, because it's definitely going to be worth at least 1 mark in the question. And so the 148 kilometres is correct to three significant figures, and so the three significant figures would take me 148 one side, well that would then be 147 and 149 as the absolute extreme values, but our upper and lower bound, well, they would be halfway in between, so 147.5 and 148.5. Those would be the upper and lower bound for the distance travelled. In terms of the petrol, that was also three significant figures. That began as 11.8, and so three significant figures, that would be 11.7 and 11.9 as the absolute extremes. But again, our upper and lower bounds, that would be in between at 11.75 and 11.85. And it says, Nathan says that my car used less than 8 litres of petrol per 100 kilometres. Could Nathan be wrong? Well, what we need to do here is he said used less than 8. So what we want to show is it possible that this could be greater than 8? And so the suggestion here is that we want to find out what is the largest petrol consumption that we could possibly get. And so if it's going to be the largest possible, then the number of litres of petrol used needs to be large, and the number of kilometres travelled needs to be small. And so we are going to take 100 and multiply it by the largest possible number of litres. And so the largest number of possible number of litres was 11.85, and we're going to divide it by the smallest possible number of kilometres travelled, 147.5. And if we do that and just type it into a calculator, we would get 100 times 11.85 divided by 147.5, and that comes to 8.033898305. Now, what does that tell us about the question? Well, Nathan said my car used less than 8, and we've been asked, could Nathan be wrong? And so we have come up with one situation where he certainly did use more than 8 litres of petrol, and therefore, yes, he could be wrong.